You're using it right now. In fact, you use it every single second you're on your computer, but you probably never really think about it. It is, without a doubt, the most important piece of software you own, and today, we're going deep inside your operating system.
I mean, it seems so simple, doesn't it? You just click, and the app opens. But what's actually going on under the hood? What's the chain of events that translates that one simple click into a fully running program on your screen?
Well, it's not magic. The answer is the operating system, the OS. Think of it like the master coordinator, the backstage manager at a huge show, or maybe the conductor of an entire orchestra of hardware and software that makes your computer actually work.
So what does this conductor really do all day? Well, its job can basically be broken down into two fundamental roles: providing a bunch of helpful services to you and your programs, and, at the same time, efficiently managing the computer's own resources. Okay, first up, let's talk about the services you can actually see and interact with. You know that beautiful graphical user interface? Your desktop, all your icons and windows? Yep, that's the OS. And every time you launch an app or save a document, or even just jump on the Wi-Fi, it's the OS in the background making all of that happen. It's even constantly on the lookout for errors to keep things from crashing. But honestly, the most critical work is the stuff that happens where you can't see it. The OS is a relentless manager. It's constantly deciding which app gets the processor's attention, how much memory each program is allowed to have, and exactly where your files get stored on the hard drive. And maybe its most important job of all, protection. It builds these impenetrable digital walls between all your programs, which is the only reason a single browser crash doesn't bring your entire computer down with it. And this all leads to a really fascinating, kind of wild idea. An application on your computer is, well, it's actually powerless. It can't save a file, it can't draw anything on your screen, it can't do anything on its own. It has to politely ask the OS for permission to do everything, and it does that using a kind of secret language. That secret language is built on something called system calls. A system call is basically a program formally knocking on the door of the kernel, that's the absolute core of the OS, and saying, "Excuse me, I need you to perform this one specific task for me." It is the only way apps are allowed to interact with the computer's hardware. So think about a single action from your perspective, like just copying a file from one folder to another. To you, it's one move, but behind the scenes, it's a total flurry of activity. It's not one request, it's a whole conversation happening between the app and the OS. Let's break that conversation down. First, the app has to ask the OS, "Hey, what's the name of the source file?" Then it asks for the destination name. Then it sends another request to open the original file and a separate request to create the new one. The real work happens in this rapid-fire loop of system calls. Read a little piece, write a little piece, over and over and over. And finally, one last call to tell the OS to close everything up. That's at least 6 distinct requests for one simple drag and drop. Now, here's what's really interesting. This whole system helps clear up a common point of confusion: the difference between an API and a system call. See, programmers don't usually write those raw system calls themselves. They use an API, an application programming interface. The API is like a restaurant menu. It shows the programmer all the available options. The system call, on the other hand, is the actual order that gets sent back to the kitchen, the kernel, to get the work done. And that little layer of separation is what makes modern programming possible without driving developers completely insane. Okay, so we know what the OS does, and we know how apps talk to it. But how is an operating system itself actually constructed? What do its internal blueprints even look like? For decades, there were really two competing designs. You had the monolithic approach, which is like building one giant, super efficient skyscraper. You put everything into one massive, super fast kernel where all the parts can communicate instantly. Or you could take the microkernel approach, which is more like a campus of specialized buildings. You keep the core kernel tiny and run everything else as separate, safer modules. So what did modern engineers end up doing? Well, they pretty much decided not to choose. Almost every operating system we use today, Windows, Mac OS, Linux, they're all hybrids. They take a fast, monolithic core for the absolutely critical stuff, but they surround it with a modular design that can load other pieces as needed. It's the ultimate compromise, giving us the best of both worlds: speed and flexibility. And now we can finally connect all these ideas to answer a very, very common question. why can't you just run a program designed for Windows on a Mac, or the other way around?
And the answer brings us right back to that secret language. It's because the system calls a Windows app uses to ask for services are completely different from the ones a Mac app uses. They are, quite literally speaking, different dialects. A request that makes perfect sense to the Windows kernel is just complete gibberish to macOS, and that's why they are fundamentally incompatible at their core. Of course, we know there are tons of cross-platform apps now. Developers pull this off in a few clever ways. They might use an interpreted language, like Python, where an interpreter program acts as a real-time translator on your machine. Or they could use a virtual machine, like Java, which basically creates a standardized, fake computer for the app to run inside of. Or they can just take their original source code and compile it separately for each OS, creating a unique native version for Windows, another for Mac, and so on.
Building something this complex, this layered, this absolutely essential, it's just a monumental task. This famous quote from programming legend Brian Kernighan really captures that challenge. An operating system is one of the most intricate pieces of software ever created, and just keeping it running correctly is a constant, heroic effort.
So there you have it. We started this whole thing with just a single click, but that one simple action took us on a journey deep, deep inside our machines. We saw the services the OS provides. We learned the secret language of system calls that apps use to get things done. And we even got a look at the architectural blueprints that hold it all together.
So the final takeaway isn't really an answer, but more of a question. The OS has evolved so dramatically, from simple command lines to the incredibly complex graphical systems we use today. But as our relationship with technology keeps changing, what comes next? What's the job of an OS when all your apps and data live in the cloud and intelligence is embedded everywhere? That is something to think about. Thanks for joining me.